Welcome to the course in stochastic processes, which is a follow-up of the course in probability theory from last semester. So stochastic processes is the next topic, and a stochastic process is something very simple actually, and it's just a collection of random variables. But there's of course more to say about this, and this course will cover some basics. For example, about constructing stochastic processes. We'll start today with some finite dimensional distributions. We'll cover martingales, Markov processes, and Brownian motion, for example. In this first lecture today, we are going to start by saying something about equality of stochastic processes and about continuity of stochastic processes. So let's get started. So let us talk about stochastic processes and their definition. As I mentioned in the intro, a stochastic process, which is here X, is a collection of random variables, which means xt is measurable. That's basically all. Usually in this course I have a probability space omega fp, which is not always mentioned, and E is the set where xt takes its values. So for example, E is very often the set of real numbers or so. Usually it's a good idea if E is Polish, which means it's a complete and separable metric space. So I rather take R and not Q, the set of rational numbers. Then sometimes I write the small omega here, and x of omega, which is the map which maps t to xt of omega, that's called a path of x, so where you fix the omega, so you fix the randomness, you call that a path. Sometimes it's the case that omega is of this form here, and you have a probability measure directly on the product e to the power of e to the power of I. Then xt is called the canonical process, but that's a very special case. Yes. Then we need something more. In the sequel, if this here holds, so the expectation of xt to the power of p is finite for all t, I say that x is p times integrable. It's LP bounded if even the supremum is infinite. We will need that at some point in the future. So let's start with some examples. Let's start simple. And let me mention that I will abbreviate stochastic process by SP for stochastic process. So maybe the simplest stochastic process is where all xt's are independent. Okay, that's not so interesting, but we had that already in the probability theory course, where we had just a family of independent and maybe also identical distributed random variables. That's also a stochastic process. So let's get a bit more exciting here. So here is an example where you can draw a nice picture also. Maybe maybe not like this, but like this. So you start your S in 0, and at every discrete time point, you either move up 1 or move down 1. Like this. And that comes about if you sum over x's, and the x are either plus or minus 1, maybe with probability a half, then the S here is called a simple random walk. So that's a very basic process. You might have also heard already about some stochastic processes which are called Markov chains. And in fact, the simple random walk here is a Markov chain. And that's defined by a stochastic kernel. So what is this? So remember what that is. So if kappa of x comma dot is a measure on this space here for every small x, and another thing was that if you fix the set here, it should be measurable in the first coordinate, but that's a minor condition. But above all, if you fix the x here, you have a probability measure on the second coordinate. That's a stochastic kernel. And that defines a Markov chain. And as I said, this here is also a Markov chain, so there must be a stochastic kernel. So we could write that down also. So let me use this, well, so what's this here? Maybe I write it down differently. I write it down differently, like this here. X plus or minus 1 equals a half. So you go from x to x plus 1 with probability a half, and you go from x to x minus 1 with probability a half. Well, and when you know this here, and that's a probability measure here in the second coordinate, you know the whole measure. So that's the measure with mass 1/2 on x plus 1 and on x minus 1. So that's the stochastic kernel attached to this simple random walk. So, okay, do stochastic processes exist at all? And I invite you to revisit, I think it was the last video from the measures theory course where we dealt with product measures on infinite products, because there is the most important theorem on this, which is Kolmogorov extension theorem. Exactly. So I'm not going to go into very much detail here. So what did we have there? We had a so-called projective family. And this is basically the family of finite dimensional distributions. That's an important concept which we'll encounter more often. So assume you have a stochastic process and you want to draw something like this here. T is here and xt is here. Then you can, of course, take a finite number of time points, t1, t2, t3, t4. And then you have something like the vector x, t1, x, t2, x, t3, and x, t4. And I call this here one finite dimensional distribution of my process x. Of course, the distribution here does not know everything about the full stochastic process. It carries less information. But this existence theorem here guarantees you when you know all finite dimensional distributions, so all of these here, so for any finite set that you have here in the index, not only of cardinality 4, but also of 5, 6, 7, and so on. If you know all of these, that defines you as stochastic process if you have one condition. So in this theorem, you start with the set of finite dimensional distributions, and you want to have the stochastic process or its distribution. And there's a consistency condition. And I could write down that like this here. So xt1, xt2, xt3, and xt4. Well, if you project this distribution here down, and maybe you want to ignore the third coordinate, then of course you must have the joint distribution of xt1, xt2, and xt4. There's another way. But if you start with a family of finite dimensional distributions, that's not necessarily the case. So what happens here, you have the joint distribution x pj here, and you project that down to some index set h, and projecting down means you just delete coordinates, and then you must end up with ph. So ph is the same as when you start with a larger index set and project down to h. And then Kolmogorov extension theorem guarantees you that there is a stochastic process, so there is a distribution on e to the power of I, such that this distribution has the finite dimensional distributions given by the family that you started with. Well, next topic is equality of stochastic processes. And you can recall from random variables, so we had also two notions there. If x is a random variable, I can have x equals y almost surely, and I could have x and y are the same in distribution, and I think we wrote that like this here. And the same concept also exists for stochastic processes. So this here means x and y have the same distribution. The only point with stochastic processes is that the first notion here, almost true equality, that might happen at one time point or at all time points at this simultaneously. So this first thing here splits in two cases here in this definition. So first of all, x and y are the same in distribution. Okay, here is another thing how we wrote that. So that's the same notation. Equality and distribution symbol there. Then we call x and y are versions of each other. So version means in distribution they're the same. Then the second thing is if at all time points the probability they're the same is 1, then they are modifications of each other. And if the probability that they're the same at all time points is 1, then they're called indistinguishable. And we will show on the next slide that indistinguishable is the strongest. From indistinguishable follows modification, and from modification follows version. Yeah. I need one more definition here, which will also play an important role, and which is a space of functions which you maybe do not know yet. So of course you know the set of continuous functions from e to I, from I to e, also you know what I will call C, E, I. Maybe I use my space more wisely here. C, E, I would be the set of all f's from I to E continuous. We will also be dealing with this space here. And the question is always the paths of my stochastic processes. Are they somewhat nice? Are they regular? Which means, for example, are they continuous? So are they in this space here? Sometimes they are, sometimes they are not. But very often they are in this space here, which is the set of functions, which is right continuous with left limits. So let me draw one example here, which we will have, I think, in one of the following lectures. We will have a process which starts in 0, stays there for a while, and when it jumps plus 1. And then it stays there for a while and jumps plus 1. And, well, at the jump time, I draw the function value like this here. And then I have exactly a right continuous function because it continues from the right, but it has left limits. And so this path here is in this set. So this here is in dE of I. And we will need that. Okay, and here's the promised theorem. X and Y are versions if and only if their finite dimensional distributions agree. At first you might think, well, finite dimensional distributions, that's much less than the equality in distribution, but it's actually not. Then, as I said, indistinguishable follows modification, and from modification follows version. But if I is at most countable, which means that you do not have something like this here, where the index set here is continuous but discrete, then they're actually the same. So from modification, I also have that they are indistinguishable. And fourth, if both have right continuous paths and X the modification of Y, then they're also indistinguishable. That's also nice. So let's see if we can prove this. Well, let's prove the first three. For the first one, we have to prove that, well, the one direction is clear. So from left to right is clear. If they're equal in distribution, of course, when you project both things down to finite time points, they're also the same. But what about the other way around? Here we have to recall also some measure theory. And the question is, so the Borel sigma, so the sigma algebra we are dealing with on this product space here, that's B of E to the power of I, what's it generated by? Is generated by, and that's basically also something I recall from the measure theory course. And it's generated by all images of finite dimensional things. So A in B of E to the power of J, and J is a finite subset of I, and finite subsets I write as subset index F. That's a finite subset. So Pj of A, I must write here, with A in some finite product space here. So what does that do here? That here is determined by A on all elements in G, and on all others I have the whole space. So that's what this set here is. And well, B of E to the power of I is generated by this thing here. That's the one thing. And this thing here is intersection stable. And as you might remember, two distributions, for example, the image measure of X under P and the image measure of Y under P, they are the same if and only if they agree on C. So equals Y is P on C. But they do agree on C actually, because C only makes something about the finite dimensional subsets here, so the finite subset of the index set. And they agree there because we know that the joint distribution of X and Y on such finite sets are the same. So, well, that was this here. Second thing was indistinguishable false modification follows version. That's, I think, not so hard. So for the first thing, so I fixed some time point I, t, then I of course have xt unequal yt is smaller or equal than, well, xs unequal ys for some s. And that's 0 because x and y are indistinguishable. I can do that for all t, which means, well, there are modifications from each other. Then if there are modifications, I can say the probability that xt1 equals yt1 ... xtn equals ytn. Well, if there are modifications, that's 1, because the set that does not happen is bounded from above by the union of the null sets where xt1 does not equal yt1 and so on, and xtn does not equal ytn. And they have measure 0, and the finite union of sets of measure 0 has measure 0, so that's also 1. And that also means that the finite dimensional distributions are the same, and that means we have proved the second thing. Exactly. Then the third, that was I is at most countable, and we have modifications, and we have indistinguishability. Let me write down something real quick. The probability that xt does not equal yt for some t. So that's basically a union. So make the union over all t, xt does not equal yt. The probability of a union is bounded from above by the sum. Probability xt does not equal yt. Okay, this here is 0, and that's a countable sum, and that's 0. And that means we have shown indistinguishability from modifications. The last thing is a bit more tricky. So the last thing was, if you have right continuous paths for both processes and you have modifications, then they are already indistinguishable. So let's do it like this. Let R be such that P of R equals 1, and X and Y have right continuous paths on R, and NT equals the set xt does not equal yt. Now, of course, it would be nice if we could argue that, well, the union over all these NTs is again a null set, and then we have it, but we cannot, because that's an uncountable union of null sets which we would need, and we do not know if that's again a null set. But what we have some regularity of the paths, so we do not need that they're the same on all of these time points. I take I prime, a different index set, which is I intersected with Q or some other countable dense subset. Then I have that the probability that, of union of NT, T in I prime, that's now a countable union of null sets, so the probability is 0. And I can write that the probability of union NT, T in all E, so remember, so this here, that's countable, that's uncountable. I can bound that from above. Okay, first I can make the intersection with R, because R is a set of measure 1 anyway. I make all t's here, and let me just write that. R bigger or equal than t, and R in I prime in R. So that means if they're not the same at some time point, because of the right continuity, we can say, well, that time point here, I can approach this from the right by time points R in I prime. And if the process is right continuous, I can find if I have something not, so something in nt where xt does not equal yt, it must already be the case that they're different at some time point r bigger than t in I prime, where they're just different. And that's what this inequality tells me. So I have the nRs here. I can replace the nt's here by nRs, and r's are only in I prime. So again, I can bound it from above, or say that's equal to R intersected with the union over R in N, R not in I, but in I prime, N R. And now I have my countable union here, and a countable union of null sets to null set, and this here is 0. Yes, since this here is a null set, and it doesn't get larger when I intersect it with something. Okay, that sounds good. Let us come to one example, which is very often a good counterexample for some things. And that's the following. That's an example of two processes where x and y are modifications, but they are not indistinguishable. And that's the following. Y equals 0, the constant 0, but x is not 0, it's 0 except for one time point, and that time point is random, for example, exponentially distributed. So the x, when I want to draw this, it stays at 0. At time point big T, it goes to 1. And then it drops down to 0 again. And as you see here, x does not have right continuous paths. Because at this point here, well, I can approach it from the right, but I do not have right continuity here. And because of this, I have the opportunity that the point number 4 here fails, which means that they can be modifications, but not indistinguishable. And in fact, they are modifications because the probability for any t, the probability that xt equals yt, well, that's the probability that big T does not equal small t, and that is 1. So they are modifications. But of course, they are not indistinguishable because they're it's almost certain that they are different at one time point, which is big T. So they're not indistinguishable. Okay, that was this example here. And I will end the video today by another important theorem, which we will need once or twice in the lecture. And let's first see what the conclusion is. So something holds. Then it says, when I start with some process x here, I can find a modification x tilde of x with continuous paths. So I want to show if x is actually almost continuous, which means I can change it a bit, have a modification of it, which has continuous paths. So that's what the T-dimer is about. And okay, there's also more to say. Almost surely Höller condition continues with some parameter here. And what do I have to check? I have to check this here. I have to check that, well, xs and xt, think of s and t very close together. So r of xs and st, so that's the difference between xs and xt, well, to the power of alpha, must be bounded by, well, if t and s are very similar, that's a small number, to the power of 1 plus beta. So alpha and beta and c are positive numbers. And I have to find the alpha and the beta and, okay, the c here, such that this inequality here holds. And that looks, of course, a bit like a continuous process, because the expectation that it makes a large jump must be so small such that it can be bounded by t minus s to something which is bigger than 1. And the proof is a bit involved, and I will walk you through this now. First of all, without loss of generality, we say our index set is the unit interval. If it's not the unit interval, we can take unions of intervals, which are almost like this here, and it will also work out. The construction is that I do take the dyadic numbers. So let me define dn. That's the set 0 to 2 to the power of n times 2 to the minus n. So which is, it starts with 0, 2 to the minus n, 2 times 2 to the minus n, and so on until I have 1. So D1 is a set 0, a half, 1. D2 is 0, a fourth, a half, 3/4, 1. D4 is 1, 8, 2, 8, 3, 8, 4, 8, 5, 6. So you get the point. And D is the union over all dn's, so all dyadic numbers. And what I will also need, which will be important, psi n, that's a random variable. That's the maximal jump the process makes between sometimes xs and xt, where s and t are in dn, which are neighbors, which means t minus s equals 2 to the minus n. So between this here and this here, my stochastic process does something. So I have a difference between xs and xt. So that's the difference it makes. And the largest difference it makes between any neighboring points here, I call psi n. And why is this a good thing to do? Yeah, I will fix the gamma here, and remember here, so here gamma times alpha is smaller than beta. So gamma times alpha, okay, gamma times alpha smaller than beta. With other words, alpha times gamma minus beta is smaller than 0. That's what I will need. I can do the following thing. I can look at the sum over 2 to the power of gamma n, psi n, and that to the power of alpha. Summing this over all n here and taking the expectation. It will become clear why I do that. Okay, expectation and sum. Well, the psi n's are non-negative, so that's everything's increasing. I can exchange sum and expectation. I can pull out here 2 to the power alpha gamma n, expectation psi n to the power of alpha. I make a basic bound, which is, so the psi n here, as we just had, the psi n here is a max, or a supremum. And a supremum of positive numbers is bounded from above by the sum of all these things. I write down the sum of n to the alpha gamma n, and then a bound from above the sup by the sum. And the supremum was over all s and t and dn, which have distance 2 to the power minus n. Expectation are xs and xt to the power of alpha. And this here I can use because that's what I have a condition for here. Smaller or equal than c times sum over all n 2 to the alpha gamma n, and well, s and t have distance 2 to the power minus n, and the c I already have 2 to the power minus n times 1 plus beta, right? And this here, so this sum here, how many summons do I have here? 2 to the power of n. Because I walk through the whole of dn and take a neighbor, okay, left, right. That's at most a factor of 2. So that's 2 to the power of n of these things here. So I have this bound. And this here is c times the sum. I see that 2 to the power of n and 2 to the power of minus n, so they go. 2 to the, and then I have alpha gamma minus beta times n. And alpha gamma minus beta is negative, 2 to the negative n, and that is finite. So that's a finite sum, as you can easily compute using the geometric series. So that's finite, and that's nice because then I know that this here is a finite and almost surely finite random variable. That's I'm using. So what we just found out, the sum over 2 to the gamma n psi n to the power of alpha is finite, almost surely. And from this I can see that psi n almost surely is less or equal than some c prime times t to the minus gamma n for all n. Why is that? Because it would be bigger than all of these here, for all n, then psi n times 2 to the gamma n would be bigger than a constant. And well, then of course the sum here, it just cannot be finite. Okay, so we have this here. But there's still some stuff to do. Yeah. I take an m and some r in in something between 2 to the minus m minus 1 and 2 to the minus m, and also the Giardi number. And then I have, I want to have something about the supremum. over R of xs and xt, xt, where s and t are in D, and s minus t is smaller or equal than R. Well, S and T are in D here. So R is in this here. So I must have because R is no more than 2 to the minus m, and they are less than this away here, which means S and T, they better be in dm, but they also be in D, which means they are in some dn for n bigger or equal to m. And I have R, xs, and xt. S and T are in dn. And I just write that here. And this supremum here, I can bound from above, again by a sum. Because here I have that both are in dn. I call this here supremum. And that supremum here, I can bound by the sum over all n bigger or equal than m. Xi n, because xi n is the maximal distance I can have between xs and xt. Now I can use this here. So that's less or equal than c prime sum n bigger or equal to m 2 to the minus gamma n. Well, and I can compute this. I can compute this because it's just a geometric series. And I find that something, some factor I call just c double prime, 2 to the minus gamma m, 2 to the minus gamma m. Well, and 2 to the minus gamma m, I can compare with what R is, and I can bound it by some c times r to the power of gamma. And I have this here now. So let's read it from left to right. So the largest distance I have between xs and xt for all s and t which are smaller than r is some constant times r to the power of gamma. And that's exactly what I need for that x here. The x here is Hölder continuous with parameter gamma. That's what I wanted to have. But it's not completely true because it's only Hölder continuous on D, because I restricted my time points here to D. So I have now found out that x is Hölder continuous with parameter gamma on D. And my x tilde is the continuous extension on whole set E. Because I can do that. I can just continuously extend the x here to the whole thing because D is dense in I. Just wait. I call it Y here in order to be consistent with the manuscript. Now I have to show that Y and X, they are modifications. That means I have some T in I and some Tn's I use. They are all in D, let's say. They're in D, Tn, and Tn, well, goes to my T. Like this. I find this because the D is dense in my E. And I have, well, that the distance between distance between xtn and xt, the probability that this here is bigger than epsilon, for some epsilon, is smaller or equal by the Markov inequality, the expectation of r xtn and xt to the power of alpha divided by epsilon to the alpha. This here is bounded from above by something times t minus tn to the power of alpha. So as n goes to infinity, that goes to 0. So as n goes to infinity, that goes to 0. And xt is the limit in probability of my xtn. On the other hand, by construction, xtn goes to yt, almost surely, by construction, because y was the continuous extension of my x at the duadic times. So that's by construction. And that means I have also that this here is in probability. And we proved once in probability theory lecture that the limit in probability is unique, which means I have two limit points here, xt and yt, and the result from probability theory tells me that xt equals yt and has probability a half. So probability that xt equals yt, because they are same, they are both the limit in probability of the same sequence equals 1, and t was arbitrary, so I showed this here for all t, and that means x and y are modifications. And that means I have proved my result. So the x tilde from here was the y from the proof. So I found the modification and the Holder continuity as well. Okay, great. We are done for today, and next time we will continue with a basic stochastic process, which is called the Poisson process. See you then.